So in the last lectures, we talked about the programmable logic design, where we mentioned that this AND array was fixed. That means the connection between the input to the AND array was fixed. And the connection between the output of the AND array to the OR array was programmable. We talked this one in our last lecture, right? Okay. So here, what is the fixed one? If you look at the circuit, we have the 3 to 8 decoder circuit. So then we have this 3 to 8 decoder circuit. We have these two inputs. We have the enable inputs, and we have these 8 outputs. 1, 2, 3, 4, 5, 6, 7, 8. So the AND array inside this 3 to 8 decoder was fixed. I show you in the PowerPoint slide, right? Then from here we get, according to our requirement, array. We call it 8 times 4 PROM, because PROM is also one kind of PRE. So here, at the very beginning, when it was come intact, all the logic function was connected. That means logic 1. All of them are connected. Then according to our requirement, we can bond to 0 to make it logic 0 according to our requirement. Okay. So what does it mean? Here, in case of PLD, depending on the number of variables, we have the output. For example, here the number of input was n equals to 3. So we have 2 to the power 3 each output or minterms. That means here minterms are fixed. Minterms are fixed. We don't need to minimize any Boolean functions because we have 8 minterms of 3 variables. Sorry. From 0, 0, 0 to 1, 1, 1. So all the required minterms are available here. We don't need to minimize the Boolean function. So if we don't need to minimize the Boolean function, that means we cannot apply any don't care condition here. So this is one of the drawbacks of this PLD, of the PROM. We cannot use any don't care condition. The second thing is, if you want to use this PROM, 8 times 4 PROM in our last example, we can design what? A full substitutor circuit. We already designed a full adder circuit, right? In case of full substitutor circuit, we have two functions. One is difference, one is borrow. In case of full adder circuit, we have two functions. One is sum, one is carry. If I am not wrong, for the difference operation, the midterms are 1, 2, 4, 7. 1, 2, 4, and 7. Oh, sorry, this is borrow, FB. For the borrow, it is 1, 2, 3, 7. 1, 2, 3, and 7. For the sum operation is also 1, 2, 4, 7. If I am not wrong. 1, 2, 4, 7. And for the carry, it is 3, 5, 6, 7. 3, 5, 6, 7. So what we can see here, whatever the function here, if I just use the 8 times 4 PROM to design a full adder and full substitutor circuit, every time we just need only how many midterms? Only 4 midterms out of 8 midterms. So that means we are using only 50%. We are not utilizing the whole circuit. So the resources remain unutilized. resources remain unutilized. So this is one of the drawback or the disadvantage. The third disadvantage of this 8 times 4 PROM is if you want to increase just only one input, the ROM size will become double. Because whenever we try to get 1 times 1 bit, it will require now 4 to 16 bit decoder. Because now here, how many inputs? 3 inputs. So it's a 3 to 8 decoder, right? So if you have increased only 1 bits, then we require how much? 4 to 16 decoder. Right? 2 to the power 4 equals to 16. 2 to 40, 16 decoder. That means the ROM size will be 16 times 4. Now it is 8 times 4 PROM, then it will become 16 times PROM. So it's bigger. So just to add only one input, the size of the PROM will become double.
4 is the output?
Yeah, 4 is the output. It's still output. Now we have function is 4. Now each function consists of 4 variables. Each function consists of 4 variables. So here now it is from 0, 0, 0 to 1, 1, 1. Each function, so 4 outputs mean 4 functions. Output of this OR gate means we have 4 functions. This is function 1, function 2, function 3, function 4. In our last example, for example, we choose this one for FS. This is FC, carry. This is borrow. This is defense. Okay? So we found 3 disadvantages. One is if you just add one input, the size will become double. The utilization of resource is 50%. Most of the cases it is not 100% utilization. And the third one is we cannot use the don't care options. To overcome these things, we have another kind of programmable logic design which is known as PLA. Programmable logic array. Today we will talk about this only. Programmable logic array. So today we will talk about programmable logic array. PLA. So in case of PLA, both here, this is PROM, right? PROM is also one kind of. So in total, we call it programmable logic design. In programmable logic design, we have PROM, we have PLA, we have PAL. So in our last lecture, we already discussed about PROM. In the PROM, this was is fixed. The input between the input to the AND array was fixed, but the OR array is programmable. But in case of this programmable logic array, both the array will be programmable. Both the array will be programmable. That means here, the connection between the input to the AND array will also be programmable, and connection between this AND array to OR array will also be programmable. So both are now programmable. Okay. In case of PROM, the previous lectures, we have n inputs. So here n inputs, we have 2 to the power n outputs. Right? In the n array, I'm talking about this array. We have n inputs, in this case n equals to 3. So 2 to the power 3 equals to 8 inputs. So 8 outputs means we have 8 minterms here. Inside, what we have? Inside we have actually the AND gates. Can you remember? The internal circuit of the 3 to 8 decoder, we have 8 AND gates. So that means if you want to implement the PROM, we should have 2 to the power n AND gates. Sorry, 2 to the power n AND gates. And we will also have 2 to the power n minterms. In case of PROM, just for example, in our last case, 8 times 4 PROM, 8 times 4 PROM, then it means here n equals to 3. So 2 to the power 3 is equals to 8. So in case of that theorem, we require 8 AND gates, and it will give you 8 different minterms. Fine. But in this PLA, the number of AND gates will be less than 2 to the power n. The number of AND gates will be less than 2 to the power n. It means then the minterms will also less than 2 to the power n. So number of AND gates in case of PLA, number of AND gates will be less than equals to the power n. So minterm will be same, will be less than 2 to the power n. Because as you mentioned, the disadvantage was in case of theorem, the equalization was not 100%. We just saw that if you just want to design a full error and a full subtractor circuit by using this theorem, the equalization is only 50%. We are using only 4 minterms each and every time. 4 minterms, 4 minterms, 4 minterms, 4 minterms. Though we have 8 minterms here, so equalization is 4. So we don't require 8 minterms or 8 AND gates. So here, this number of AND gates or minterms is less than 2 to the power n. Of course, then whenever you require less AND gate, it will cost you less. Okay, it will cost you less. The size will be smaller. The power consumption will be smaller. So everything will be beneficial for us. Okay. So then, what about the OR gate? The OR gate array, we can have n number of OR gate. In this example, we have 4, right? So we can have n number of OR gate. Now let me remove these things. So we will have 2 to the power less than 2 to the power n AND gates, and then we will have n number of OR gates. So what does it mean? So depending on the requirement, the PLA, how much our requirement is, how many functions we have to represent, depending on that, the number of OR gates will be chosen. So each output of the PLA, each output, so this is my output, each output of the PLA is the result of sum of product. Is the result of sum of product, SOP. The output of the PLA, output of programmable logic array, is the sum of product, SOP. And the number of OR gates, how many OR gates is required, is determined by the number of output the PLA needs to produce. Each OR gate will represent one function. Each OR gate will represent one function. Because this side is almost similar, right? We are programming here. In case of theorem, we also program the OR array, so-called OR array. Now the number of AND gates is smaller than the previous one, but we still have the OR gates here, so programming. So each OR gate will represent only one function. Okay. So if the PLA has OR gates, and it can implement n different inputs of n variables, we can say. If the PLA has n number of OR gates, so it can represent or it can produce n number of functions with n number of variables. So n is my input, n number of inputs, and n number of outputs. So let's try with one design. So here we program both the AND array as well as the OR array. This is the main difference between the theorem and PLA. So today we are talking about the PLA, the second kind of the programmable logic design. In our last lecture, we talked about the program PROM. In PROM, my AND array was fixed, my OR array was programmed. Today, we are talking about PLA, programmable logic array. Here, both the AND array as well as the OR array will be programmable. Let's try to understand with one example with the design. I am designing a 3-input PLA. So here n equals to 3. For example, n equals to 3 and n equals to 2. And this will have two OR gates, two functions, and each function will consist of 3 number of input variables. Let me design first, then I will discuss. Let me draw first. Oh, sorry. Maybe you can see here. I can see. Okay. So as we are telling that we have 3 inputs, we have A, B, C. We have 3 inputs. These 3 inputs are given to a buffer circuit. This circuit is known as buffer circuit. Buffer circuit is something like that. The internal circuit or the internal circuit diagram of the buffer circuit is actually a 2 inverter circuit. It means you give an input A here, you will get A bar here, right? So you will take output from here, then you give this A bar to another inverter circuit, you will get A here. So you can see here we have a bubble and we don't have a bubble. We call it a true form, this is a complementary form. So we will get a complementary form here, A bar, and we'll get a true form of A. One is true form, one is complementary form. This is a buffer circuit. Internal circuit diagram of the buffer circuit. This circuit is known as buffer circuit. So it means that we are giving 2 inputs and it will give you 6 inputs to the OR gate. In this case, this is the output. Actually, for the circuit is there, will provide 6 different inputs. A bar, B bar, C bar. Okay? So here, this is for example A bar. So this is A, this is B bar, this is B, this is C bar, this is C. So this is my, as I mentioned here, we will program the AND operation, AND array as well as the OR array. Okay. Then the output will be connected, or this input will be connected to AND gate. And as I mentioned here, in case of PLA, the number of AND gate or the number of minterms will be less than 2 to the power n. Here, in this case, we have 5 AND gates. So, if I draw this one, let me draw other color. I'm not sure how I can manage that space. We are giving now. So here we can program the AND array. In our previous circuit, when it was 3 to 8 decoder, the AND array was fixed. Now we can actually control the program the AND array here. So the output of the AND array is the minterms. So it will give you 5 minterms. As you have 5 AND gate, it will give you 5 minterms. These are the 5 minterms. Okay? Then how many outputs we have? N equals to 2. We will have 2 outputs. So now we can program here AND array. We can program here the OR array. So this is the circuit of the 3 to 2 PLA. 3 inputs, 2 outputs PLA circuit. But previously, if you can remember, to design 8 times 4 PROM, we had 3 inputs, but in that case we have 8 AND gates. That means we have 8 minterms. But out of 8 minterms, we just need to use only 4 minterms to design the full adder or full subtractor circuit. So 50% utilization. We don't need to use all the 4. But here we have now 5 minterms, 5 AND gate.
How do we have 5 minterms? Because 2 to the power n is going to be 8.
That's why I mentioned. So here it will not following the, in case of programmable logic array, whenever here we are not required, because in case of PROM, the AND array was not programmed, that was mixed. So that means we have maximum 2 to the power 3 equals to 8 minterms. And we have minterms and we have 8 AND gates, right? But in case of PLA, we are actually programmed the array, AND array as well. So by programming the AND array, we can reduce the number of AND gates. Because we already said that if you want to design by 8 times 4 PROM to a full adder circuit or a full subtractor circuit, we don't actually need all the 8 minterms. On top of that, if you have the 8 minterms, that means you don't need to minimize the Boolean functions. Whatever minterms is, we can use that one. If you don't need to minimize the Boolean function, that means we cannot apply the don't care conditions. Sometimes it is good for us because when we do the K-map, can you remember the K-map? We have the don't care condition. Sometimes if it is required, we can use. If it is not required, we don't use. But here you cannot use this don't care condition.
In this example, can we use, for example, 6
Yeah.
amps or 7 amps?
Yeah, less than 2 to the power.
Less
So
than
here
2 to
2
the
to
power
the,
n.
less than equals to 2 to the power n.
It just has to be less than.
Less
2 to the
than.
power.
It has to be less than.
We can use any amount
Yes.
less than. Okay.
Okay. So now, so we can say here AND gate array is programmable. This AND gate array is programmable, right? Here I can write down AND gate array is programmable. Here I can write down the OR gate array is programmable. By default, all the connections will be given. That means, if you think, so how many inputs for AND gate? Each AND gate? Each AND gate will have 1, 2, 3, 4, 5, 6. Each AND gate will have 6 inputs. Each AND gate. By default, all the connections will be given at the very beginning. That is logic 1. If you think about that programmable logic array, we have the fuse from the source to the column line. They will become intact. Intact means logic 1. By default, it will come as an intact, the logic 1. Then according to your requirement, you can pass a very high current to bond to make it logic 0. So by default, all the connections will be given. All the connections. Each AND gate has 6 inputs here. A bar, B bar, C bar, each and gate. And all the OR gates have, each OR gate has how many inputs? 1, 2, 3, 4, 5. So it will also be given. Then according to your functions, we can bond to make it logic 0.
Can you explain this one more time?
Okay, of course. So here, in this design, we are just trying, just an example, okay? We just make that we have 3 inputs and 2 outputs, that is 2 functions. So to make a 3 inputs, in case of PLA design, we will use a buffer circuit. This is known as a buffer circuit. The buffer circuit will give you both the true and the complement output. A bar, B bar, C bar. Inside this black box or the block diagram, we have this circuit. We have 2 inverter circuit. You give input A, the first inverter will give you A bar. You can take output A bar, a complementary form. Then if you give it to the next inverter circuit, the output of this next inverter circuit will give you A, which is 2 form. So the bubble shows you the complementary form, without bubble is now 2 form. We give A, we get A bar and A. We give B, B bar and B. We give C, C bar and C. That means in this case, we have 6 inputs. 6 inputs. These 6 inputs will be connected to the AND gates. Here we have 5 AND gates. That means it can give you 5 different minterms. That means each AND gate has 6 connections. A bar, B bar, C bar. At the very beginning, the connection will be there. That means fuse will be intact. Now depending on your function, you can bond to make them logic 0. At first, all of them in the logic 1 state. Then output of this AND gate. So this is programmable. In our PROM, this array AND array was fixed, but now it is programmable. Now here it is the output of the AND gate. This is the minterms. The connection between the AND array to the OR array. Connection between the AND array to OR array. So as we have 2 output here, so we have only 2 OR gate here. Each OR gate have now 5 connections. 1, 2, 3, 4, 5. That means 5 minterms. At the very beginning, all the 5 minterms will be connected. Now depending on your function, it will bond the other. So these are connections. So I'm just showing only one. Actually all of them are default. By default they will be connected. By default all are connected. Okay? So this is the basic structure of a PLA, 3 to 2 PLA. So we can mention that this PLA consists of 3 inputs, and 3 inputs are given through the buffer circuit, and the buffer circuit will give you finally 6 inputs. All these 6 inputs will go to the each AND gate. All the 6 inputs will go to each AND gate. Each AND gate have then how many inputs? 6 inputs. A bar, B bar, C bar. These inputs are programmable. Okay. So what about the output of AND gate? At the beginning? What are the output of the AND gate at the very beginning? Anyone? At the very beginning, we didn't program. Intact, everything is intact.
1.
What is the output of AND gate? He said 1. Any other? 0. Okay. How many of 1? How many bought for, what is your name?
Cheyenne.
Cheyenne. How many bought for Cheyenne? Only 1 bought? How many bought for Zeren, right? He wins. He got 4 votes. Yes, it's 0. Because we are giving A and A bar. So A and A bar means A is 0, A bar will be 1. 0 times 1 equals to 0. It's an AND gate. So all the output of the AND gate is at the very beginning is 0. Because what is AND gate? So we have 6 inputs AND gate, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So A bar, B bar, C bar. So if A equals to 0, B equals, A bar will be 1. 0 times 1 will be 0. So everything will be output will be 0. Okay. Now, what you can do, we can do some designing, right?
I have a question.
Yeah.
You're giving 3 input, we are getting 2 output. How?
Yeah, because this is called a buffer circuit.
I understand, like let's say A is equal to 1, B is equal to 0, C is equal to 1. What's the expected output?
No. So it means that what we have, this is the maximum possible, right? Either A can be 0 or 1, B can be 0 or 1, C can be 0 or 1. So we have all the options. We have either 0 or 1. So these three inputs, A, B, and C. For example, the sensors. We have 3 windows here. So we have 3 sensors here. So either it will be open or it will be closed. Or when it will be closed, we can say that it will give you logic 1. When it will be open, it will give you logic 0. So you have to have the 3 windows, 3 sensors, all the options. So like this, so A, B, C. So 3 windows, when it is closed or open. It is closed or open. Is it closed or open? Close this one, open this one. Close this one, open this one. Like this.
And what's the result of the output?
So now, here, so if you design like this, so what will be the end game? If any of the window is open, it will become, according to your design, if you want to make an alarm, that if the window is open, I need a green light or green LED to turn on. So that means you have to give some voltage, the logic 1. So if you want to create the logic 1, then you have to design like something like that. So then it will create logic 1. So it will see, for example, this is for the windows, and this is for these 2 doors. Then, so you have to make function. If any windows is open, this LED will turn on. If any door is open, this door is turned. Okay, is it clear? Okay. So by programming, we can remove some of the interconnection. As I mentioned at the very beginning, all the connections are given. According to the program, according to our requirement application, by programming, now we can remove any of this interconnection. That means we can apply some high amount of current, it will burn your fuse. Can you remember the pyramid? We have the fuses between the source and the column connection. If you can remember, we have because inside logic, we already have all of the MOSFET, metal oxide semiconductor, right? The MOSFET, we have this one. Can you remember? Sorry, this is JFET. So for example, this one. So this is my drain terminal, this is source, drain terminal, source terminal, drain terminal, source terminal. Then here we have this fuse with the column. At the very beginning, they are intact. If you apply a huge amount of current, the fuse will burn. It will become logic 0. So by programming, we can remove some of the interconnections and can implement specific product meters. So here in this specific PLL, we have how many? Just for example, we just choose, we have 5 AND gates. So, okay, 5 AND gates and 2 outputs dimension here. So either we can get the true form and the demo. And finally, I don't have any space here, but I will show, for example, I take this output from here, okay? This is the continuation from here. Output of the OR gate. If I draw with the black pen, continuation from here, okay? So we have the OR gate. We have these 2 OR gate. These 2 OR gate will be given to 2 XOR gate. Let me draw it first. It will be given to 2 XOR gates. This is an XOR gate, right? So XOR gate have 2 inputs. What about the other inputs? Other input will be something like that. So why we use these 2 XOR gate? If you want your output in true form, what is true form? True form is logic 1, complement means logic 0, or A bar. So true form is A and complement form is A bar. If you want your output as a true form, then we will apply the other input of the XOR gate will be logic 0. Logic 0. What is XOR? A XOR B. A bar B plus A B bar. Right? So if you give A XOR 0, what it will give you? A bar 0 plus A B bar, right? So it will give you, okay? So if you want the output in a true form, you have to connect the another input to logic 0. If you want to get the complementary form, you will connect to logic 1. So A XOR logic 1. So A bar dot plus A dot 0. So it will give you A bar. So we have two functions. We will get that two function either in true form or in logic in the complementary form. If you want to get the output in a true form, the another input of the XOR gate will be 0, logic 0. If you want to get your output in true form, complementary form, the another input to the XOR gate will be logic 1. So this is so here I may mention, sorry, I don't have any space here. I put this star here, that means we are starting from here. So these are the OR gate, then we have to do this. So it is possible in case of PLA, we can just separate them. One will be true form, one will be the complementary form. So in PLA, since the product term, in the PLA, we can tell this is disadvantage, surface is advantage. In terms of if you want to compare with the 8 times 4 PROM, it is advantageous. Because in case of 8 times 4 PROM, we saw that the utilization is 50%. Resource utilization is 50%. We have 8 min terms, we have 8 AND gates, but we used only 4. So in that case, we just only do, if you want to, again, simple, same, if you want to design the full ladder circuit or the full substructure circuit, we just need 4 min terms. But in case of 8 PROM, we have 8 min terms. That means 50% utilization. Now we have 5 min terms. So utilization is at most 90%. So in that case, we can say it's an advantage. But here is still, as we have a lower number of midterms, so we have to minimize the output. In case of PROM, we don't need to minimize the output because we have 8 midterms, we have 3 inputs, we have all the combinations from 0, 0, 0 to 1, 1, 1. So we have all the 8 midterms with 3 variables. We don't need to minimize here. But here we have 3 inputs, but 5 midterms. So that means we have to minimize the midterms. So what another thing we can do, we can think on here, since the AND operations is shared with between 2 operations. This is operation 1, this is operation 2. For example, this is for carry, this is for sum. Or this is for difference, this is for the borrow. Both the output of the AND operations is sharing. Because the output he is sharing with this OR gate, also with this OR gate. So that means we can find the common midterms which is useful for both the functions. Again, I'm repeating this my sentence here. We have this output, a midterms. For example, this is midterms ABC. Okay, this midterms is ABC, just for example. This ABC is useful for both the functions. So that means this ABC is common. So we can say that, then that midterms we can share the function. For that particular function, this midterms is shared by the both functions. We need to find out their common functions. Sorry, common midterms. So once we do one example, it will be more clear to you. Let's try to design or let's try to use this circuit to implement a full substructure circuit. Okay, a full substructure circuit. So in the post-substituted circuit, let me write down the table here. So we have A input, B input, and the borrow input B in. So it is 3 inputs. Zero, 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 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, right? These are the possible inputs. Okay, so now I can write down this is borrow in. So what are the two outputs? One is difference, another is the borrow. As I using the same circuit, it has 3 inputs and 2 outputs, 2 functions. So here we have 3 inputs, A, B, and borrow, and we have 2 outputs. One is difference, another is borrow. If you look at the truth table for difference and borrow, if I go here. For the difference, we have one logic high for these 4 midterms, for these midterms, and we have logic high for borrow for these midterms. So for difference, we have high for 4 different midterms. So we can write down function difference is midterms 1, 2, 4, 7, 1, 2, 4, 7. For borrow, we have 4 midterms 1, 2, 3, 7. 1, 2, 3, 7. Right? 4 midterms. So to implement this one by using this circuit, what we need to do at first? We need to minimize the Boolean function. This is the first step. Because we don't have 8 midterms, we have only 5 midterms, so we have to minimize the Boolean functions. So, and try to find the common products. So what are the Boolean functions for borrow and carry? If I write down the expression for the borrow, if I write down the borrow, which is A bar, B bar, B in plus A bar, B in bar, B in bar plus A bar, B in plus A B in. If you take common A bar, B from here, A bar, B, so it is B in bar plus B in from these two. If you take common B in there, it will be A bar, B bar plus AB. Right? If you take common A bar, B, it will be B in bar, B in. If you take common B in here, so it is A bar, B plus B. So it will cancel each other. So A bar B plus B in times A x bar B. So here we can only minimize only 1 midterms. We can minimize only 1 midterms. If you, this is for borrow. For the difference, this is for borrow. For the difference, actually, we cannot minimize because difference is A XOR B XOR B in. We cannot minimize this one. Okay, fine. So this is the first step. We need to find out how much we can minimize the Boolean expression. Now, if you want to implement this borrow input, we have 3 product terms. We have to borrow how much product terms? 3 product terms. and for the difference, we have 4 product terms. If you just expand this one, we can see it will have 4 product terms in case of difference, and in case of borrow, it has 3 product terms. So 3 plus 4, 7. But we have only 5 entities. We have only 5 entities. So then the next step, we need to find out the common. Is there any minterms that are common for both the functions? Of course, we can see here 1, 2, 7 are common for both functions. In case of difference, minterms 1, 2, 7. In case of borrow, we have minterms 1, 2, 7. So that means these 3 minterms can be shared. So 1, if I mark these 3, so 1, 2, 7, 1, 2, 7. So 3 minterms for 3 entities, another minterms for 4, another minterms for 3. So by using the 5 minterms, we can implement. Okay? Now we have to give the connection. That means
Can you
at the very
explain that
beginning.
again?
Sorry?
Can you
Yeah, sure. So as I mentioned, to implement the borrow circuit, if you expand this equation, we have 3 product terms. That is 3 minterms. Here in difference, we have 4 product terms. So if you want to implement them to separately, we need how many minterms? 7 entities. But here we have only 5 entities. So how we can implement by using the 5 entities? So the first step, as I mentioned, we have to try to reduce. Once it is not possible, that we'll go for to find out the common minterms which are common for both the functions. If you look at the minterms here, this is function for difference, this is function for borrow. Here function for difference, we have 1, 2, 4, and 7, these are the minterms. And here for the borrow, 1, 2, 3, and 7 is the minterms. So out of there, 1, 2, and 7 are common for both cases. So these 3 minterms can be shared. So for example, this is 1, this is 2, and this is 7. These 3 minterms can be shared. So how many remaining? 4 and 3. So we can give 4 and 3 here. So by using the 5 AND gates, we can implement this. So now we have to give the connection, right? As I mentioned, at the very beginning, all the connection will be given. Now you have to, by programming, by bound, you have to take out the logic one. So, but for here, we're just removing here. Usually, by default, interconnection actually given, but for here, will be the opposite one actually. We just think that there is no connection, we are giving the connection. Okay. So, the first one, this one, 0, 0, 1. That is A bar, B bar, B in. A bar, B bar, B in. Which is A bar? This is A bar. So A bar, I can make the black color. A bar, then B bar and B in. This is B bar and this is B in. B in is this one.
So these are not connected.
These are connected now. And that's what I'm telling you. By default, the interconnections are there. By programming, we remove. But here I cannot make it that one. So I'm doing the alternating one, opposite one. For example, we think that there is no connection. According to the program, we are giving the connections. So to get these minterms, which connection we need? A bar, B bar, B in. A bar, B bar, B in. So this is B in now. This is B bar. And this is common for both the borrow and the difference. So we'll give in both we are programming here, we are programming over. What will be our next midterms?
For which are 0.
Second one, right?
Alright.
So A bar, B, B in bar. A bar, B, B in bar. A bar, B, B in bar. If I make mistake, please let me know, okay? So this is A bar, then we have B bar, sorry B, this is B, and then we have B in bar. B in bar. Both the midterms are given for both the functions. Sorry, the same midterms is given to the both the functions. So we have to connect the both. What will be our next midterms? This one, which is A bar, B, B in. A bar, B, B in. A bar, B, B in. But this one is given only to borrow, right? This is always given to borrow. For example, we choose this is my borrow. This one is my borrow. This is my difference. Okay. The final midterms is not the final. The next one is this one, which is A, B bar, B in bar. A, this one, A, B bar, B bar, and B in bar. This is only given to difference. This is only given to difference. And the final one is 1, 1, 1. That means A, B, B. So this is A. That means we connect the two form. We have to connect the two form. We have to connect the two form. And this is also given to both. Very clear? Now, I mentioned, what about the output? We can take our output as a true form. Yes, sir. Oh.
Sorry.
Oh, I think you are asking me a question. Then I
No,
think,
no, no.
yes, you are okay, you are good. Yes. Then I get wrong. You didn't mean yes or you didn't mean no. You are
I
exercising.
have one question. How does the I'm confused about three product and the 4. It's like
So these are the mean terms, right?
yeah.
Mean terms. The product terms or mean terms. So 1, 2, and 7. What does it mean? This is 1. This is 2. This is 4. So midterms M1. So this is M0, M1, M2, M3, M4, M5, M6, M7.
I understand that concept.
Okay.
But what's the borrow 3 in 3 product and difference is 4? What is that?
Oh, this one. This one from here. So as I mentioned, if you have the expansion, what is the total? This is the total Boolean functions. So the first step we should try to reduce this Boolean function because we don't have all the 8 midterms. We cannot express. So we have to make the all applying by all the laws, the De Morgan's theorem, so we can try to minimize. Then we can implement. To implement this borrow, we need 3 product terms. Here this one, another is this one, another is this one. 3 product terms. Here, if you want to look at the difference, if you expand this equation, A XOR B XOR B in XOR, then you can see to implement this difference, you will need 4 different midterms. Okay? So now, as I mentioned, the last step, your output can be in true form or your output can be in complementary form. If you want your output in true form, you should connect logic 0. Logic 0. If you want to get your output at a complement form, you should connect at logic 1. Okay? If I'm not wrong, yeah. To get the true form, it will be 0. To get a complementary form, it will be 1. So for example, here, we give this.
You're talking about the last circuit you designed, this one?
Yeah. So I'm drawing again here. So I'm drawing again here. So So this is the output of the OR gate. Output of the OR gate. So this was my D. This is my B. They will be given to XOR gate. Okay, so still it is D, it is B. So for example, we want our borrow. So as I mentioned, we can connect the another input like this. So if you just, this is logic 0, this is logic 1. If you want to get this function at true form, what should we connect? Logic 0. So if you want to get the true form, this is logic 0, right? So we should connect this one. Also we can extend this line to get the logic 0.
If you want to get true form in D,
Both. It's up to you. If you want to get both the true form, you can connect logic 0. If you want to get both in the complementary form, you can connect logic 1. And if you want to, then no, I want this one at true form, and this one is
to get value.
Form. Yeah. So it's just 5 volt or 2 volt to get logic 1, or you can apply 0.2 volt to get logic 0. So this is the overall circuit for a full substitute circuit. Now I think you can apply this same concept to design full adder circuit. If I ask you in the exam to implement a full adder circuit by using a PLA circuit. So this is the result. You have to make sure the truth table. Then from the truth table you can find the minterms. Then you can find which minterms are common. Then according to this one.
You don't need the equation, right?
No equations required here. No. Usually in the data sheet, for example, if you have the PLA circuit, they give some truth table here. For example, they mention that this is the PLA circuit, PLA IC, and this is the truth table. Here you can see these are the minterms. So this is A bar, B bar, C, A bar, B, C bar, A bar, B, C, A, B bar, C bar, A, B, C. Same. So here, this is my input then. And output here, what does they mention? So what is it? Are you taking your output in true form or in complementary form? If your IC is giving you a true form, they will mention T. If they are giving in complementary form, they will mention C, something C. So they will mention the IC will give you either in true form or in complementary form. Okay. Another thing in the output, if the output is logic high, they will give you just 1. If the output is not connected, so here we have not something is not connected here, so they will give dash. So this is not important. This is just for idea. If you read the data sheet, how to read the data sheet. Okay. Okay. So here in my we have time, so we can try. Then I will show you the example. So implement a full adder circuit by using the PLA. So I'm giving you 5 to 10 minutes. You just draw the circuit and truth table. If you can remember at first what is the step, just write down the minterms for full adder circuit. In the adder circuit we have two functions. One is sum, another is
carry.
Write down the minterms first for the sum and carry from the truth table, then just implement it. Let me remove these things so that I can prepare. So let's match with these minterms. Do you have the same minterms? This is for carry, this is for sum. Is it all okay with me? For sum, 1, 2, 4, 7. For carry, it is 3, 5, 6, 7. Right? So here we can see only one minterms is common, the 7. Only one minterms is common, 7. So that means we need how many minterms? 7 minterms. Out of 8, one minterms is common. In total, we need 7 minterms. But we have only 5 candidates. How we can implement? How we can do? There's a little twist here. Instead of combining midterms for carry 3, 5, 6, 7, we take it the midterms, right? 1, the logic 1, not high. Instead of that, we can take a max term. That means we can combine 0, 1, 2, 4. 0, 1, 2, 4. So here, what we'll do, a twist, we'll take 0, 1, 2, 4. Okay? 0, 1, 2, 4. That means we are taking FC bar. We are taking FC bar. 0, 1, 2, 4. If you take these things, what will happen now? We have 1, 2, 4, it will become common. So we actually taking the invert. Then the output we have options to make it again a complement. So that's why this is the options. At the beginning we have 3, 5, 6, 7, 1, 2, 4, 7. We can see just only one midterms is common, 7. So that means we mean 8 midterms, 7 midterms, but we have only 5 and 8. What we can do, instead of taking this FC, we can take FC bar. So FC bar will become now 0, 1, 2, 4. So now we have 0, 1, 2, 4 and sum is 1, 2, 4, 7. Then we can see here we have now 3 common midterms. One is 1, 2, 4. And then we have 0 and 7. Right? So if we look at, so we have now fs equals to 0, 1, 2, 4, 7 and fc bar is equals to 1, 2, 4. So if you take later on double bar, it will give you fc, right? Later on we have that portion, we have that options in our hand. We can do the complementary form. So if you get the complementary over complementary, it will give you the 2, 4. So we get back our FC. So don't worry. Now, according to your truth table, you have to give the connections. What is the first connection? Is 0. So A bar, B bar, C in bar. A bar, B bar, C in bar. So this is A bar. Let me take another color. A bar, B bar, C bar. So this is A bar, B bar, C bar, and this will give it to the what? Carry. So for example, this is my carry, this is my sum. So we are giving here this connection. What is our second midterms? 1, right? 0, then 1, M1. So this A bar, B bar, C in. A bar, B bar, C in. A bar, B bar, C in. And this is given to both. This is given to both. This is given to both. Then what is our second midterm? This one. A bar, B, C bar, A. C bar. A bar, B, so this is my B, and then C bar. A bar, B, C bar. This is also given to both. So this is also given to both. The next one, which is my midterm here, this one, this one, this one, this one, and 4. 1, 2, 4, 4. 4, which is this one, this is 4, right? So A, B bar, C bar. A, B bar, C bar. And this one also given to both. This one also given to. And finally, we have which one? This one, ABC. This is A, this is B, this is C, and this is only given to sum. It is only given to sum. But here we have made a twist. Instead of FC, we take the FC bar, right? So this FC bar is this one. So this is my FC bar carry. This is my FS sum. So here this is carry, this is sum. So we make it a complement form. To get the complement form, we have to connect to logic 1. So now this is my logic 1. We connect this one, and we connect this one to logic 0. Sorry, my mistake. So we have logic 1 line, logic 0 line. Let me try again first. 0 line and 1 line. Here this is the carry, this is the sum. Now, for the sum, we need the true form. To true form, we have to connect to logic 0. This is logic 0. For the carry, we have to complement it. So we have to connect to logic 1. Because for our simplicity, we complement it, FC bar. So now if we take the double bar, it will give me FC. So here we are getting FC bar. If you complement it with the logic 1, we get FC. And this is FS. So this is how we can implement the logic function, the Boolean functions, any circuit by the array, programmable logic array. So here we program the AND array, we program the OR array. Here. Any questions? So I will upload this one. You can read this one more. If you have any questions, you can talk to the next class.
I have.
Yeah. Thank you. No, no, it's fine.
So can I draw it like this?
So here is, so we have 2 lines. So we have drawn 2 lines forward. So whatever you need require. So if you require 1, you can take the connection here. If you require 0, you can connect it here. So what if you connect like this, for example, this is 1, right? This is 1. For this you can go, this one. But we have to have the options for this one.
I have just one way.
Can you wait for me?
Yeah.
So as I mentioned, so if you expand this line, so what is the product? Our product is A, B, B, C, C, B, this is the product.
Yes.
So here you can see this is a product. So here if you expand this one, there will be another two products.
Yeah.
So run 3 products.
Yeah.
In the difference, if you expand this AX of BX of in excess, we can found there will be 4 products.
Oh.
That was me.
Okay, you have a question for me, you can
You had all.
wait for me, I can talk to you.
This month.
Yes, sir.
Right.